In this series of videos, we're going to talk about a mathematical object called a matrix. Now, a matrix is basically a table of numbers, but it can be used when a single number isn't going to be good enough to represent information. So one common example of something that we could represent with a matrix would be a results table from, say, a sporting competition. So here we have a pretty typical looking table. We've got different teams and we've got number of wins, losses and draws that are recorded. Now, this is a good way of presenting information, but mathematically we can't do much with this. So when we take a matrix, basically we could represent this data in a matrix by basically getting rid of the columns and the row labels. So getting rid of the labels and just representing the numbers and arranging them in a grid. So in this particular case, we could represent this table of numbers as a matrix like this. So the first row would have 8, 1, 1. That represents Draco's performance. Hydra would have, this next row we have 4, 6, 2. And this next one would be 5, 2, 3. And the final row, and I'll actually redo the brackets in a second, 2, 1, 9. Like this. Now, if we want to describe the type of matrix that we got, we can describe it based on the number of rows and columns. So in this particular case, we've got 4 rows, 1, 2, 3, 4, and we've got 3 columns. And when we talk about matrices, we always describe the number of rows before the number of columns. So we would call this a 4 by 3 matrix. Now, once we've represented it in this form, there's a bunch of mathematical processes we can do to analyze this information that we wouldn't be able to do if we kept it in this original shape, this original table form. So this has put that table into matrix form. Sometimes though, we might have things that don't look like a table that we want to represent as a matrix. So this here is an example of a network. A network is just a series of points that are joined by lines. So this could represent any number of things. They could be connections of pipes in a system. They could be cities that are being joined by different roads or something like that. So we could have a matrix that describes how these different points are joined up. Now, to do that, we might want to represent it as a table first. And that's how usually I would do this. So let's list our points: A, B, C, D, E, and A, B, C, D, E. Now, if we represent this here, what we're going to do is we're going to use a 1 to mean that 2 places have a line connecting them. Okay, we'll pretend they're cities. So a 1 means that there's a road connecting 2 particular cities. A 0 means there isn't. So let's have a look at each road. So town number A, is town number A connected to A? Well, there's no road that kind of goes in a loop connecting it, so no, it isn't. It gets a 0. Is A connected to B? Yes. Is A connected to C? Yes. Is it connected to D? No. E? No. Okay, and then we can go through again. Let's think about town B. B is connected to A and C. It's not connected to itself. It's not connected to D or E. And then we can go on like this. So C is connected to A, B, and D, but not to itself or E. D is connected to C and E, and nothing else. And E is connected to D, but not any of the other towns. Now, once we've done this, we can actually just get rid of this row here. And we now have represented this map as a matrix, which can be very nice for then doing analysis on that map. The particular matrix that we have here is a 5 by 5 matrix, 5 rows, 5 columns. It's actually what we call a square matrix. Okay, for obvious reasons, it's square. And in fact, this particular matrix is also has a special name. It's what's called a symmetric matrix. Symmetric just means it's symmetrical. Okay. In other words, if I were to draw a dotted line down this, what we call the main diagonal, you would notice that everything here is a mirror image across that line. Okay, so you can see here everything lines up as a mirror image across that line. So this particular matrix is called a symmetric matrix, but you don't have to worry too much about that. The important thing is that we can represent these kinds of results in matrix form and then perform certain processes on them.